Okay, so welcome back after the coffee break. I think we'll start with the second part of the scheduling session. It's being given by Adam Wierman from Caltech. And I think Adam will talk more about the bridge between competitive, or rather worst case and stochastic analysis through like robust, efficient doing system design.
Perfect, thanks. So yeah, so as Nikhil said, I mean these are two fields that are in some sense really related, really close. They work on exactly the same problems, but in another sense are very disparate. There's very few people that publish in both of them. There's very few connections between them, and so our talks are kind of examples of the few connections that we know of between these fields and how you can try to exploit those. And so Nikhil did the quick background, and one example of this connection where you tried to get a best of both worlds from taking a worst case analysis and porting it over to the stochastic setting. And I'm going to try to focus on two other examples where in different ways the results from the two fields kind of inform each other and can actually combine to get something different than either field was doing alone. And so the perspective behind these combinations in the second part is really about robustness versus optimality, and this is the way that I view these two fields. So when you're doing a competitive ratio, you talk about optimality of the competitive ratio, but really you're trying to say this is the most robust policy in some sense. It's the best worst case bound you could get. So these are robustness bounds, and if you're doing well, if you give an example of a policy that has a good competitive ratio, it's a robust policy. It may not be optimal for the particular situation you're using it in, but it's going to be very robust. And the perspective in the stochastic community, the queuing community, is a little different. It's saying, we know something about our situation, we can model it, and now let's try to actually write down what the optimal policy would be for that particular setting, for those particular model assumptions. And so really the focus is on optimality in this world, rather than robustness. But of course, both are important in practice, and sometimes they're aligned. So the SRPT example that Nikhil gave is something where you're optimal and robust, right? You're one competitive, so they're really perfectly aligned. But in most cases, they're not. So the blind examples that Nikhil gave are cases where they're really not so aligned on the surface, right? So if you want to be robust, RMLF, this policy that he talked about at the end, is the best, most robust policy. You get this log n guarantee. But if you want to be optimal, RMLF is not optimal. If you know that the workload, the job sizes are Pareto, you should do SETF. This is provably optimal in a queuing model. If you know that the workload is light-tailed, you should do first come, first serve. This is provably optimal in a stochastic model. And so there's a distinction, there's a contrast between the type of policy you should use if you're trying to be robust across all the workloads versus if you're trying to be optimal for a particular workload. And I think this difference in perspective is what drives a lot of the different questions and the different styles of results that the two communities go after. So I'll try to connect those in this talk with two examples. And I guess, like I said, these are two examples. Now, they're the only ones I know of. Partially that's because I've worked in both of these areas, but I also know the queuing literature pretty well. And there's really very few places where there's a strong connection between these fields. And so I'd love to find other connections. And part of us doing this tutorial, why Anupam asked us to do it, is that hopefully during this semester we can find other places where there are connections between these two large, robust literatures. But in these two, there's, in some sense, success stories. And the idea, I guess, to give the kicker first is, Nikhil showed how to get the best of both worlds. This first example, take a worst case result and port it over to a stochastic result. The first example here is going to basically show how you can try to combine results from the two fields to actually get an explicit trade-off, results that can quantify how much you suffer in terms of robustness to get optimality and vice versa, and how you can kind of optimize combinations of the two. And the second one is going to look at a place where scheduling is just a really hard task, and there are lots of inefficiency, hardness sorts of guarantees. And the idea is to show that you can get a lot of insight into what's leading to these guarantees by combining the stochastic and the worst case viewpoint. And so you can get a new sort of perspective from that. So I dabble, I have a side of me that's a system side, so you'll have to bear with. I actually have motivation slides for my models, so sorry, I'll go quickly. But the first little example is power, and energy is important at all levels of systems these days. So power is why we have multi-core. Battery life is important. I've done a lot of work in data centers and energy, and so I could give you lots of fun statistics there. But maybe the kicker is electricity usage of data centers is growing 10 times faster than the rest of our energy usage, and so we need to do something to curb it. But anyway, I'll skip over that. The takeaway is, the old perspective on scheduling and these sorts of things and all of these levels in computer systems was just faster is better. And nowadays, there's an increasing willingness to trade off speed, trade off how quickly you're doing things with how much energy you're using to do them. And why this trade-off exists is because basically the faster you run a system, the more power it uses. And there tends to be some convex relationship between power and speed. And so you pay an increasing cost to run faster. And this is, where you sit on this is an optimization that you're making to trade off energy and performance. And so speed scaling is the generic term that you use to capture this. So you can dynamically adjust the speed of your system as it's running to trade off how quickly you're serving jobs with how much energy you're using. And naturally you'd say, if there aren't too many jobs around, you can run slower. If there's a lot of jobs around, you should run quicker because you're incurring a lot of costs. Every job is including extra delay, so you run faster when there's a lot of jobs there. So there's a natural sort of way you would go about doing this. And this is something that happens in different forms at all levels of systems. So at chips, it's voltage or frequency scaling. Disks can spin down and park and run at different speeds. Wireless, you have dynamic transmission power, which changes depending on what jobs are present and how you use it, all the way up to data centers where you change the number of servers that are active, the number of racks that are in power saving modes, et cetera, depending on the workloads that are present. And so this is sort of a very generic thing. And you can think of studying this at its core as just a very simple scheduling queuing type question, where you have a server with jobs arriving to it. And you need to dynamically figure out not just how to schedule the jobs, but also what speed to run the server at. How many servers to have on, or some things like this. But when one server, just what speed to run it at. And so this is the speed scaling decision. And of course, it's very intertwined with the scheduling decision. Right? So scheduling will tell you how many jobs are there, and how many jobs are there is going to impact how you should scale the speed of your server. Question? Oh, no. OK. OK, so the question now, for doing speed scaling, you're dynamically controlling your speed. You're doing this to balance energy and performance. So we have to have some metric that combines these. Sort of the main one, I guess, the initial one that people have studied the most, and this is across OR as well as in computer science, is just a linear combination. So you take a weighted combination of I'm using T for response time or flow time, just like Nikhil did. So you take a weighted combination of that and the energy that you use. Of course, there's lots of other measures that you could study as well. You could take a constrained version where you're minimizing flow time subject to an energy constraint. You could take the opposite where you minimize energy subject to deadlines or QoS constraints for your jobs. And basically, all of them have been studied to some extent. And there are lots of open questions remaining on all of them. But you name your measure, somebody's looked at it to some extent at this point. And it's, these sorts of models have been studied since the mid-90s, basically. And I guess I should say, I'm assuming everybody knows energy, but energy is power over time. So when you start to think about what this measure looks like and to drill down into this model a little bit more, you have this power function. And just, again, since I'm a practical guy, here's real data from real processors that we measured. And there's lots of versions of this. But basically, if you look on a log-log scale, things look rather linear, which means that when you're thinking of chips, a polynomial is a pretty good model for what this power associated with the speed looks like. Disks have a similar sort of polynomial. Wireless, you get something exponential. But it doesn't matter. Just think of this as something convex and increasing. Now, for this talk, I'll assume everything's nice and continuous and easy. But of course, in reality, there's often discrete states. And again, there's lots of papers that have looked at the discrete versions of these problems. So don't take my not talking about that for meaning that it doesn't exist. OK, so that's our simple model. And now, if we think of what might happen in this, let's just look at some examples. So the simplest example is batch job arrivals. So suppose you just have n jobs arrive. I'll order them in terms of their size. And there's nothing else that's going to come. What do? You're going to try to schedule them in some order. Well, everything from the previous two talks should say we should put the small job first. But now, how should we determine the speeds? We should probably run quicker at the beginning than at the end, because at the beginning, while we're working on the smallest job, there are n-1 jobs waiting behind us. And so all of them are paying cost while we're waiting. And then we sort of slow down a little bit as we finish the jobs. But what should those things be? So just, first order optimization. It's not just intuitive that you should use SRPT. If you think about it for a minute, you can prove to yourself that if SRPT was optimal for a single server, then here, again, it's optimal. Because imagine fixing your speeds, whatever speeds you decide to use, fix them. And now SRPT will be the optimal thing to do. The other simple thing to convince yourself of is the speeds shouldn't change in between moments when you complete the jobs. There's no incentive to change that. The optimal will have constant speed in between the job completion moments in your system. And once you make those, you can actually just write down the cost. So you can write down the combination of the cost as, for the first job, I'm going to run at some speed Sn. So Sn is the smallest one. It's going to take Xn over Sn time. During that time, I'm going to be incurring power P of Sn. So this is kind of the response time for the first job, the power for the first job. The second job has to wait for the first job to complete, and then it gets to go. It takes this power while it's going, and so on. Right? So you can just write it down nice and easily. Then the next observation is you can factor out all the sizes. So the sizes don't matter. All that matters for the optimal speeds in this example is the number of jobs that are present, which makes things a little bit easier to think about. And then you can actually figure out what the optimal thing would be. So to keep the formula simple, take polynomial. And then your optimal speeds for this example turn out to be this alpha root of n over alpha minus 1, which, when you think about it, is really nice, because it's saying that the power, so if there are n jobs in the system, the speed that you should run at is so that the power you're incurring is proportional to the number of jobs present. So in some sense, you should balance the delay penalty, the number of jobs that are being subject to delay while you're there, proportionally with the power that you're willing to run at. And this is something that is a pretty clean observation. And on the system side, it's something that, this is a paper from Google that was back in the early 2000s that really made a call for the community to try to use energy proportional computing. They weren't using this model to do this. They were just saying this is a nice thing. We should be able to have systems that run with 1/10 of the power and energy if we're running at 1/10 of the load. This was something that they really called for, and it aligns with what theory says here. But it's not always optimal. This was one little example. So the next simplest example that you look at when you're thinking of scheduling problems is, instead of a batch, a periodic arrivals. So one job arrive every 1 second. So let's have a job of size 1 arrive every 1 over r seconds. Again, we'll keep SRPT, but it doesn't matter, because the optimal should just be finishing everything before the next job arrives. So you run just fast enough at rate r so that you finish the job that you have before the next job arrives. So every job waits 1. You're always incurring this power. Just to make things simple, I'll look at the cost per job, so I'll normalize by r. And then if we were to do energy proportional scaling for this, we'd be in some sense screwed, right? Because before we could get up to running at rate r, we'd have to let our jobs queue up, right? Or p of r jobs queue up, because we're proportional, right? So we have, if it's going to be useful, if it's going to be worth it for us to run incurring power r, then we have to have p of r jobs waiting. That's what the idea of energy proportionality is. And so that means that you're already giving up a factor of 2 in this really simple case. Because now you have PR jobs waiting for you, and you're using time PR. So you're off by a factor of 2 in what is, probably the easiest case to schedule, right? Just finish things before the next job arrives. But despite that, energy proportional scaling always is pretty close to optimal. And it's something where this idea, SRPT, P inverse of N, was proposed by Kirk Pruse and co-authors back in 2003, just without an analysis at first, actually. And then basically in the next 7 years, the competitive ratio was generalized. So initially the results started for unit-sized jobs and quadratic power functions. Then it went to polynomial power functions. Then it went to general jobs, and so on and so forth. And finally, the end of the day, you got down to the 2 for general power functions, not even smooth convex, just general power functions, and arbitrary sized jobs. And so in some sense, this policy matches its lower bound in that previous example, but it's even, I guess, better than that in some sense, in that there's no policy that can do better than that. So it's not just where the progression ends for SRPT and this energy proportional scaling. There's no online policy. Well, I should hedge. This is one of my results, so I can criticize it. We have a really ugly condition here on the algorithms that I'd love for somebody to remove. So we can show that basically no natural algorithm can do better than a factor of 2. And this is one of those kludgy proofs where we can show it for any policy that's going to serve one job at a time, or any policy that has speeds that grow slower or faster or proportional to asymptotically. But some sort of weird oscillation in the speeds asymptotically might, in theory, be better. But the thing is, so we get this too. And so if we interpret this result, basically, you see that compared to the non-energy case, you can't be optimal anymore. You have to give up something, but you don't actually have to give up that much. And it's a very simple, intuitive idea of the speed scaling that, when combined with optimal scheduling, gets you there. And actually the proof of this theorem kind of builds on the 2 examples that I just showed. So those 2 examples are enough to show no policy can do well for those 2 examples, or no natural policy. Okay, so that's kind of the baby version of speed scaling. And there's lots of ways that it is and should continue to be pushed. So lots of other ways you can imagine balancing energy and performance, going from single to multi-server systems, going to more complex models of scaling where you take into temperature and more detailed models of what the system might be, what the power function might look like. But to connect with what Nikhil was talking about, I want to focus a little bit on these non-covariant, these blind policies. Because there we had this, he talked about there being this hard bound where non-covariant policies couldn't do better than log n competitive. And here that goes away. The fact that you can pay attention to energy actually gets you, makes the problem easier for blind policies to do well. And in some sense, this is a connection to the resource augmentation results that he was mentioned. So, if with the blind policies, he mentioned that if you give them a little bit extra capacity, they can do much better. And well, if we're willing to sacrifice a little energy, we can give blind policies a little extra capacity. And so that trade-off is worth it. And you can sort of make up for policies that aren't quite as good by paying a little bit in the energy cost. And so the nice thing is the same speed scaling actually lets you do this. So you don't even have to change the speed scaling. You can still stick with energy proportional speed scaling. And then non-clairvoyant policies can do very well. So the first result on this form was from Chan and Pruse, and I think Nikhil might have been on that too. And they got a 2 alpha squared over ln alpha. And then at the end of a bunch of results, we have one that's for 4 alpha minus 2. I think that's the best known among blind policies right now. But there's not a tight lower bound yet. What you know is that there's no blind policy that can be constant, independent of alpha here. So as alpha goes to infinity, blind policies all do very badly. But I don't think we have a tight lower bound. Certainly not one that matches the 4 alpha case. But the nice thing about this result, I think, compared to the previous ones, is that it's for a very common policy. So PS, processor sharing, is this round robin-like policy that Nikhil talked about. And it's something that's really often the model that people use for systems in practice. It's a very typical kind of scheduling policy, and it does very well. And it's one that connects very nicely with queuing results, which we'll see in a second. And like I said already, this is a nice comparison because in the non-energy case, when we just cared about flow time, PS was order n over log n, so basically order n competitive, so as bad as possible. And all of a sudden, with a little extra, speed based on the speed scaling, it can get down and be small, constant competitive. So for the realistic case, alpha is about 2 in chips, and so this would be 6 competitive. And again, like the other case, there's lots of interesting results here. But I don't want to dwell on that because I want to get to the connection. So that's kind of the story about speed scaling from a robustness perspective. And here, things don't completely align because we're not getting one competitive results. We're getting policies that are very robust. They have constant competitive ratios. But there's a natural question of, can you actually be optimal in a stochastic model? And how do the policies that are optimal in stochastic models, when you're willing to make assumptions about the workload, connect to policies in the worst case model? And so here we have this idea that this kind of speed scaling works well. But over here, who knows? And so basically, the model now just changes very slightly. So instead of having no assumptions on the workload, we throw in our MG1. So we have a Poisson arrival. We have job sizes that are generally distributed. We have some load. And we have the same objective. And here, actually, this becomes, if you look at PS, where we ended on the previous section, this becomes a real textbook stochastic control problem. You can pick up any intro control theory book. And one of the examples when they're doing MDPs will be this problem. And it's a nice problem because you write down a very simple Markov chain for PS. This is exactly the top half looks exactly like what Nikhil had on his slides. And now the only difference is the bottom half, instead of all being μ's, is your controllable speed. So these are your control variables that you're trying to optimize, and you're trying to minimize this cost by setting those. Write down the MDP, use whatever numerical tool you want, solve it. Done, right? So this is the way the textbooks give it to you. If we want to try to connect it to the worst case results, we have to do a little bit more because we have to actually get structural results about the form of the policies that result, and that turns out to be pretty grungy. But you can do it, and so this is our best attempt at it. And the middle line, so this is MG1, this is processor sharing, this is the quadratic case to keep it simple enough to put on a slide, although we have the general. And this middle line isn't so interesting. The relevant one is this bottom one, where if you look at it asymptotically, you get rho plus root n. And remember, this is the quadratic case. So this root n is P inverse. This root n is energy proportional scaling. Yeah.
So how is energy defined? There's no finite horizon anymore, right?
Yeah. So think about it as, when I wrote down that example, I normalized it per job. Think about normalizing it per job. Yeah. So was there?
Always at most 1?
No, so here, that's a good point. So here, rho, I don't care about it being less than 1, because whatever the arrival rate is and the job size is, arrival rate times job size is my rho. The speeds are monotonically increasing, so it just means that you'll go up and have an occupancy high enough that it stabilizes. So there's no instability here. Whatever the rho is, as long as your speeds increase to infinity, you'll stabilize it. So none of that matters. Okay, and so you can get this, and the nice thing about this is that we have this result, which provides a pretty strong connection to I guess a superficial, but a direct connection to the worst case, because we have this additive thing where you have the load, which is a very stochastic component, combining with exactly what you would suggest from the worst case perspective for this model.
So would the interpretation here be that your speed of processing tasks has to grow as square root of the number of jobs you have?
Yeah. And I mean, I should say that there's a big difference here in the sense that for small n, root n is not the right thing for the stochastic model. But for large n, root n, which is, asymptotically you're growing at root n, and this is what the worst case model suggested for this case. Yeah, and the nice thing is, so this is PS and this is MG1. You can push this. So there's been a couple of papers now that have done GG with fluid type scalings for other policies. And basically, once you go to a fluid type scaling where then the policy doesn't matter too much, and you can get rid of these assumptions, but it's an approximate model. And you basically get exactly this asymptotic form for other policies, more general models.
Should I understand what fluid type scaling means?
No, so Nikhil had it on a slide. No, so fluid scaling, so basically it's a way of looking at a Brownian motion approximation for what the queuing system looks like. I mean, you can think about that. You can think of,
Is the worst case the intuition for what fluid 100% sample parts look like the worst case?
No. Yeah. I'll say something about that in a second. Yeah, so, okay, so coming to this, now I'm going to actually have a plot on a slide about some results. So if we look at this, we have now the natural question that a systems person would ask is, how valuable is this stuff? So what is the difference between these? And so what I'm showing you here is the cost per job. And there's basically two regimes that you care about. And so this is log scaled on rho over beta, but this is low load or low energy cost, high load or high energy cost. And basically, if you think of what you're gaining from speed scaling, this is how much you're gaining. And this is interesting because it lets you look at questions such as, that result I just showed you was for PS. Suppose I did it for SRPT, and we tried to look at how much scheduling mattered. In the worst case result, scheduling matters a lot. It matters by a factor 3 or 4. Yeah, so beta was the thing that for the theorems is all 1. It's the weighting of energy. Or sorry, the weighting of delay. So the objective is beta times E of t plus this. So for the theorems, it's all 1, but here it's relevant, so I brought it back. Thanks. So now if you're looking at this, you can prove a lower bound, and you can actually show that in some sense there's not much room to be gained from doing anything more complicated than processor sharing. And this is borne out when you look at doing SRPT instead of PS. So you get very, very small gains on the particular instances once you're in the stochastic. And it's even worse than that in the sense that if you didn't want to do dynamic speed scaling in the way I've described it, and all you wanted to do was turn off the server when there were no jobs present, and when it's on, have a constant speed. So this is called gated static. So you don't do anything complicated. You just say, I'm going to turn it off, and I'm going to run at a constant speed, but I'm going to be a little bit smart about how I pick that speed. Then you're basically the same. You can gain a little bit from doing the very complicated speed scaling that we spent all this time so far talking about, but not very much at all. And this brings us back to my theme of robustness versus optimality, because if all you care about is a small epsilon approximation in the stochastic model, there's no reason to do full-on dynamic speed scaling. Just pick an optimal speed and turn off when there are no jobs present. But if you care about robustness, there's a huge reason to go after these more sophisticated schemes. And so to drive that home, what I'll do here is I'll show, this is the real row. I picked a system where the load was 10. But we'll imagine that you don't know that, and you have some estimate of it, and that's what's on this axis. Okay? So if you do the optimal stochastic control, and you know the row, it's the best. But if you're off, there's kind of this degradation where, depending on how far you're off, your cost is worse. And so your robustness is captured by how much this increases compared to what it is at optimality, which is here. If you do gated static, you're really, really fragile. Like if you underestimate that speed, you can be if you underestimate the load, you can be unstable. If you overestimate, you pay really quickly. And now, the worst case model is basically here. So the worst case model corresponds to, we don't care what the load is. There's no load in that model. And it turns out that it aligns, in this case, exactly with the rho equals 0 case, right? Because in the quadratic case, the optimal stochastic control was rho plus root n. The worst case control was root n. And so they align here. And so you basically, it's as if you just chose rho equals 0. And you tried not to estimate it. You were really conservative, and then did your control based on that. And so this is kind of the story. So you have robustness here where you don't depend on the load at all, but you pay in terms of optimality. And this may be large, or here. And the nice case about speed scaling is that strong connection we had between the form of the control in the two models lets you actually prove results that combine them directly. So this was a result from, I guess, one of our papers. I didn't write down the year, but it's 2011. And so this is just for the quadratic case, but we can do it more generally. the exercise is to imagine designing a policy that's optimal for some estimate of the load. So you're going to estimate the load in the system. You're going to design the optimal stochastic control policy for that, but you want to know how robust it is. So you want to know the competitive ratio for that policy. And then you're going to use this to decide how to control for both your suboptimality and your robustness. Okay. And so what you can do is you can prove that if you designed your system for load rho, you're 2 rho plus 2 competitive. So in some sense, it gives you a direct comparison between how accurate you are in your rho. So that the difference between this and the true rho gives you how off you are for the optimality, and this gives you your robustness guarantee. And you can trade off explicitly between optimality and robustness because you can combine, in some sense, the worst case results for the stochastic policies. Yeah.
So for the rated static case, the algorithm uses the rho estimate to decide the speed at which to run when the server is on.
Yeah.
And there is no max.
Right, and there's no max because if you underestimate rho, the competitive ratio would be infinite because if you underestimate, it's unstable. And so any of the discrete settings, anything that's not as robust, you don't get a nice constant here. But here you get a robustness bound that depends on your estimation for rho, and in some sense this highlights exactly why you should be conservative in your estimate for load in setting these stochastic models. Because if you're conservative, it helps you with robustness. If you're aggressive, it hurts you with robustness.
So, yes, a natural next question would be that can there be like a policy that only adjusts the speed at 2 levels of?
Yeah. So can you do something where you're 2 levels or n levels and still maintain something like this? I don't know. It's a great open question. Another one is, can you get something that is independent of rho? Right? Can you have a policy that has an optimality guarantee in the stochastic model, but has a robustness guarantee independent of rho? No result that I know there.
How sensitive are these curves to the initial? You had the cost function in terms of those exponents, right?
Yeah.
The convex form that you have.
Yeah, so the only way, this result assumes polynomial. I don't know how to do it beyond polynomial. It's pretty sensitive. So you get something that's growing in alpha here. That would be another thing that would be nice to reduce. Okay, and so in this case you get a 22, a 2, and a 6, and so you could actually trade off and be within 1 and only have a 6. So is the dependence on the rho needed? All these sorts of things. The one comment I'll make on this is, if you only care about robustness within the stochastic model, not worst case robustness, there is something you can do. And it's interesting because it means moving away from energy proportional computing. So if you give up on worst case entirely, but you want to be robust within MG1 type assumptions, then linear scaling can be too competitive and not use the rho at all. So you don't have to estimate rho. You're always within a factor of 2 of the optimal, but it's under stochastic assumptions still. And this is the sort of result that I love to see, that connecting the worst case and the stochastic model. This is pretty weak. And this is really, this doesn't hold beyond quadratic. This is a really baby sort of result. But it's an indication that maybe something's possible more generically. OK. Good. So that's basically the end of what I wanted to say on speed scaling. But I want to highlight that results like this are interesting beyond speed scaling. Pretty much pick your scheduling question. There's a disconnect between optimality results in stochastic models and robustness results in worst case models. And finding a way of trading off between those is something that I know of basically this result and one other one that I've seen that happen. OK. So the second one I want to do is a complete change of pace onto tails. And the idea here is, instead of trading off between robustness and optimality with deriving a trade-off, I want to say, OK, we can't do well in this situation, but can we understand better how to design an adaptive policy, how to learn where the hardness is coming from by combining the insights from the 2 types of analysis? OK, and so here, tail. So what do I mean by tails? This is like the 95th percentile of performance, 95th percentile of delay. So instead of caring about the mean, as everything that Nikhil did and everything that I've done so far does, we look at these, we tail. And this is this is the measure of interest really for most systems. Doing well in the mean is nice, but really all QoS guarantees are about the 95th percentile or the 99th percentile, things like this. The mean is not what you care about. And there's that's one motivation. The other nice motivation, again, comes from the Google folks. And they have this nice paper just a couple of years ago on the Taylor scale. And basically the perspective is now everything that you're doing in Hadoop or these big multi-parallel systems, if all your jobs are running in 100 parallel servers, then the 99% bad event happens every time, or almost every time. And so that's the bottleneck now. So rather than being something that happens rarely, it happens on every job, every time. And so you have to control the tail to do anything. So again, older, faster is better, minimize the mean, now cut off the tail. And so again, SRPT is optimal and robust for the mean. Can you hope for something that's optimal and robust for the tail? It seems like a small change. Basically, the answer is no. You can't hope for that. You can't do well for the tail. And that's the short answer, and I'll give the long answer now. So that's the short answer. Now, the long answer, what do we even mean when I say optimizing the tail? So what do you mean control the tail? And so there's basically two lines of work in this. So you either focus on minimizing higher moments, variance, third moment, et cetera, or the LP norms of response time as a general way of saying that, or you focus on the tail, but you can't really focus on the 95th percentile, so you focus on the decay rate of the tail or the asymptotics of the tail. And basically, this is the focus of the scheduling community. This is the focus of the queuing, although there are some queuing results up here too. But of course, this isn't something you can look at in the worst case model. And there's other things, but these are really the two big ones. And so starting with the LP norm, because worst case is more familiar, and the story here is shorter. Basically, the story here is no policy can do well. You are in your worst case, you get order n competitive policies is the best you can hope for, and this is Nikhil's result. And that's kind of it. But just like with blind policies, a little extra capacity goes a long way. And so if you give yourself 1 plus epsilon speed, you can be 1 over epsilon competitive. And this is independent of the p's that we care about. OK, and so there's lots of people that have a long line of work on these, some of which are in the room. But maybe the question that is interesting coming out of that is, why is it so hard to be robust for LP norms? I mean, we can do well for the mean. Why not for L2? And I think you see examples, right? Clearly, these proofs have some instance that the algorithms do badly on. But when you give one instance as a lower bound for a proof, it's very fragile, right? It's hard to learn something about really what the underlying hardness is from. And I was quizzing Nikhil about this yesterday to see if he had some intuition about. He didn't have anything for that.
So what is the simple model that the result is for? Is it
exactly a single server model that we talked about?
Like MG1? Or
No, this is just worst case. So this is worst case. Yeah. So these are worst case results. Now we're going to go to stochastic, though. So now the question is, can maybe the stochastic model give some insight into why these are actually hard, and maybe something that you can do to learn about debating around these? Yeah.
Hardness result is for everything. Can you just try?
Yeah, for everything. OK, so in the stochastic case, this is actually a region where we can do GG. So we can be pretty general with these because all we're looking at is the limit for the tail. We don't care about exact analysis. It's already approximate. And so we can do arbitrary or stochastic arrival process, arbitrary job size distributions. Here I will care about load being less than 1, since we're not controlling the speeds. And the goal is to minimize the asymptotic of the tail. And basically, the first step here is to realize there's 2 regimes of interest. Basically, either things behave exponentially or things behave polynomially, and you can't analyze them the same way, and different things happen in these 2 regimes. And so basically, as soon as you have light-tailed job sizes, your distribution is going to be something that decays exponentially. As soon as you have heavy-tailed or polynomial job sizes, then your response time is going to be polynomial as well. And so you need different tools, different techniques in both cases. And I think something that'll be nice to pull out for especially the worst-case folks here is, well, so these are the particular ones. Is that the intuition across these is very different. And so what I like to sort of pitch here is that in some sense, when you're thinking about this type of large deviations analysis, you're basically studying conspiracy theories. And when you think of the heavy tails, you're thinking about catastrophes. And this intuition gets you a long ways in analyzing policies in the stochastic model, and also in randomized algorithms too. And so I don't think it's as familiar to you guys. So to get you an idea of what I mean by conspiracy and catastrophe, so here's a little thought experiment. So suppose you're giving a lecture, you have 50 students. For kicks, you do a poll. You ask them to write down their heights. You ask them to write down how many Twitter followers they are, and then you sum them up. Okay, and so turns out that the sum of heights is something maybe 300 feet, and the sum of Twitter followers is like 1 million. So both are pretty weird numbers, right? So these are extremes. Something strange happened. To get 50 people that have heights that sum over 300 means that the average is over 6 feet. Something strange happened. It's rare. I don't know how many Twitter followers you guys all have, but I doubt we'd get to 1 million in this room. And so, something weird happened, right? And if you think about why, now do the thought experience. So why? What could have led to this? So with the heights, well, maybe Twitter first. So with the Twitter followers, if in this room, if this happened, it's because somehow somebody here is a Twitter celebrity. There's one person that probably has 1 million followers, and the rest of us have our 10, and then that's that, right? Zero. Right. There's a lot of zeros. There's a lot of ones, twos, right? But here, that doesn't happen, right? There's not some giant that's 290 feet tall and the rest of us, right? So, in this case, probably like the volleyball team or the basketball team was in the room. They were all really tall, and, that drove it. Whereas here, it's a celebrity. So this, we have a catastrophe, right? There's one really big bad event. And here, there's a conspiracy. There's a lot of slightly larger than average events that combine to make the rare event. So this is conspiracy versus catastrophe, and this underlines all of it. And you can formalize this. So you can formalize mathematically what this means by a conspiracy principle and a catastrophe principle and use them in proofs directly. So that, just to make it a little bit more mathematical in the example, and I like this plot a lot in terms of driving it home. So Weibull distributions, hopefully everybody's heard of them. Maybe not. So Weibull, oh, nobody knows Weibull? Who knows Weibull? Just out of curiosity. Good, that's some. So Weibull is a nice distribution because it can be both heavy-tailed and light-tailed just by setting the parameter. So if you set its shape parameter less than 1, it's heavy-tailed. If you set it equal to 1, it's an exponential. If you set it bigger than 1, it's light-tailed. Okay, and so it's a nice thing for comparing the two distributions. If you take that away, that's one thing you learned from the talk, so that's good. And so let's take 2 Weibull samples. And we'll both mean 1, and we'll assume that a rare event happened. You added them up, and the sum was some really large number d. Now, as a basic probability test for you, so if it's exponential, so Weibull with parameter 1, and you know that the sum was d, what's the marginal of x1? A nice property of the exponential is that then x1 is uniform between 0 and d. Right, so they're, once you know that the sum of them is d, they're both uniform. Either one could be large. They're basically the same. Everything's nice and simple. Now, I push it to the light-tailed version, or sorry, I think I do the heavy-tailed. I push it to the heavy-tailed version of Weibulls. I can see a catastrophe principle. So once you have the heavy-tailed version of Weibulls, one of those was d, one of them was 0, basically. D minus epsilon and epsilon with extremely high probability. I push it to the light-tailed version. They were both right at the mean. So this is what we always use in our randomized algorithms concentration inequalities proof, right? We have a large sum. They're both close to the mean. There we go. But I mean, I guess I shouldn't say mean. They're both close to half of d. All right. And so very different behavior. So here you have a conspiracy. They're both much larger than their mean because the one would be down here. But they both are contributing to the bad events. Whereas under something heavy-tailed, only one contributes to the rare events. And so formally, this is what you can mean. You can write them down as. So there's two versions that are both useful for catastrophe principle. The max has the same asymptotics as the sum, or given the max is larger than t, or sorry, probability that the max is larger than t, given that the sum is larger than t goes to 1. So they're basically saying the same thing. So that's catastrophe. Basically, a sum is large because one thing in the sum was large. And this happens under things like Pareto, Weibel's, log normals, things like that. Conspiracy principle is the opposite, and it's the more intuitive version. If the max is large, the probability that the max is larger than t is much less likely, order of magnitude less likely than the probability that the sum is large. Okay, so catastrophe principle, we use it all the time. What I'll show you how to use it for in a second is, principle of single big jump is basically the way it comes up in queuing a lot, where because if the workload got large, it was because one really bad thing happened, one really large job arrived. But generally, the catastrophe principle is associated directly, so it's one-to-one with sub-exponential distributions, which are defined in this way. So these are equivalent. It takes maybe 5 lines to prove it, but it's not too hard. And they encompass basically every heavy-tailed distribution that you've heard of. So if you've heard of it, if it has a name, it's sub-exponential. Now, it's not all of them. There are things that are heavy-tailed that are beyond that. And actually, in my talk on Friday, long-tailed distributions will come up, so as a little trigger. But everything that you've heard of is sub-exponential. OK, so that's conspiracy versus catastrophe. Now, I want to give an example of how you use them. So we'll do FIFO, just because it's easy to do here. And so we'll start with heavy-tailed, because catastrophe is more fun. So the tail asymptotics of heavy-tailed look like this. And I didn't write down an attribution because it's basically one of these results that's just been known forever. So Nikhil did the residual. I used XRES instead of XE, but this is the residual that he talked about connecting to the inspection paradox. This, remember, was the number of jobs in the system as the expectation. And so this has some nice meaning in terms of intuition, but I won't dwell on that too much. So it's waiting time instead of response time. Residual job size. The only thing I'll say is that this is really bad. So it's hard to tell without context. This is a bad result. This is actually the worst case that you could have for your tail asymptotics, because if you think of things as being polynomial, remember this was the definition that Nikhil gave. It's if you integrate a polynomial in this way, you're getting something that's 1 degree heavier than the job size distribution. You'd like to be scheduling things so that the tail was matching the job size distribution. This is a whole degree heavier. This means it has 1 less finite moment. So this could mean something where your mean was finite and the tail, this is really bad. So this could mean that this is a bad news result. And it's in fact not just bad, it's the worst possible. So proving it though, the one result, the result that's maybe the most direct to what I've told you about conspiracies is this proof. So you have to trust me on this queuing result. It's a beautiful queuing result. It says that the workload in the system can be decomposed into just a geometric number of residuals. And so this actually comes from doing an analysis of processor sharing. That's quite nice and uses reversibility and things like this. But it's a very classic result. So take that as given. And now once you have that, you can write down the tail just directly from this. As saying that it's 1 minus rho times rho to the n from the geometric times the probability that the sum is large. Catastrophe principle is about sums, so I just now apply it directly to that sum. And the catastrophe principle tells me that this sum is large because one of them was large. And now I just compute, and I'm done. Okay, so it's sort of directly, not so intuitive, but it's directly thing. More sample path one, and so this one requires this, which is MG. Sample path, you can get to GG. And here we use this principle of a single big jump that I talked about. So here, the way to think about it is what has to happen for us to have a really large delay for a job? Well, it means that the workload has to be really large at some time that a job arrived. Right? So a new arrival at time 0 has to wait behind all the work that was there. So for the waiting time to be large, this has to be large. Well, how could that have gotten large? Well, one way it could have gotten large is that at some time in the past, a really big job arrived. And on the surface, this seems like a ridiculous thing to try to do a proof on, but catastrophe principle tells you that this is basically enough. This is the dominant event. If you can analyze this event, everything else will concentrate around it. And so that's all you do. You say, I'm going to consider a simple path where a really big job arrived. How big? Well, work gets done at rate, work will get cleared out of the system at rate 1 minus rho t, because new work is coming in at rho t. So I need that job to be x plus 1 minus rho t size. And since it's really large, law of large numbers will kick in, and this will be exactly right for what we need. We'll get tight concentration around it. And so we just have this big jump, and that's it. So it's a little bit of work to give your upper and lower bound, but basically you write down this equation, which says that I need some job to have arrived at some point in the past that was this big. I integrate over the different times that that job could have arrived. I do 2 lines of calculus, and I'm done. Now, the lower bound is really easy because this is one way it could have happened. There are many other ways it could have happened, so bounding the fact that those don't contribute too much mass is where you use some concentration stuff. But this is the argument. So that's catastrophe, and you can see it's really useful. So now, if you ever have a heavy-tailed queuing system or heavy tails come up, you just, this is the intuition. A bad thing happens because one really large thing happened, and as long as your heavy tails are sub-exponential, that lets you do the analysis directly based on that principle. Now, conspiracy is much more familiar. So this is the way that you all do your concentration results for randomized algorithms. So the results here tend to be a little bit more, more difficult to parse. And so this is what the tail index looks like. It's the SOAP. This is the MGF, moment generating function of the interarrivals. This is the moment generating function of the job sizes. It's not so important what it looks like, but it's optimal. So in the heavy-tailed case, it was the worst possible tail. Here, it's the optimal tail that first come, first serve obtains. And what I want to say here about the proof is just to connect it to the conspiracy principle and to make sure that everybody's here has heard of Cramer's theorem. So Chernoff bounds, of course, you've used before. For these sorts of analysis in queuing, you use Cramer's, which is just the strengthened version of it. So you don't need a bound. You don't need just a bound. You need the tight asymptotics, and so you can get the tight asymptotics with basically the same form as long as you just look at the limit rather than look at the finite bound. Okay, so once you have that, one of the most famous queuing equations is Lindley's recursion, maybe second after Little's law, which somebody already asked a question about. And so this just says that the waiting time under first come, first serve for the n plus first job can be written in a nice recursive way based on the waiting time that you had for the nth job, plus the size of that new arrival minus the interarrival time, the time since the previous job to arrive. Right? This is how much work was done before you arrived, then you added this to it, so this is the new workload, and of course it has to be positive. So this kind of defines the whole dynamics of the workload for a queuing system in a nice simple recursion. And you can get rid of the positive part by just looking at the max of subsequent sums, where the sums are over the xi minus the ai's, the gap between the interarrival and the x's. And now you have something that looks pretty nice. So you have this probability that's the max of sums. And so union bound, or not union bound, but bound the max with the sum. And now you can apply Cramer's to the internal sum, contraction principle to the whole thing, which basically says that the sum is going to be bounded, the tail of the sum is going to map to the smallest decay rate of any piece of the sum. And the key thing is that you get your conspiracy principle here because which of these sums is going to dominate? Basically, you're going to get a dominant sum that includes some intermediate n. And that intermediate n means some combination of a certain number of jobs was a little weird. So you have a large queue length, not because there was one big arrival, but because there was some sequence of n intermediate jobs which combined to make things bad for you. And so you basically get exactly the conspiracy from understanding what this minimizer of this contraction principle looks like. Okay, so with that in mind, so we did we did FIFO, and FIFO is worst possible in heavy-tailed, optimal in light-tailed. Now we're going to get back to the connection with it's impossible to be robust, because if we go through the laundry list of scheduling policies, you'll see that they're all either worst case in light-tailed and optimal in heavy-tailed, or vice versa. So if you were to do the same analysis for SRPT, you would get worst possible for light-tailed, optimal for heavy-tailed. SETF, the best, that blind policy that Nikhil talked about, worst possible over here, optimal over here. You can go down the list. Basically, every policy you've heard of has been analyzed, and it is optimal or worst case in both, and nothing is good across both of these regimes. And so it begs the question, can a policy be optimal for both? And of course, the easy answer to this question is yes. You just learn the workload. And if you know the workload, you use the right policy for that workload. Not very satisfying to a worst case crowd, I would imagine. But so the more natural question, can a static policy be optimal for both? And here, the answer is no. So, and it's because of the inability to control for catastrophes and conspiracies at the same time. So you can take exactly that intuition about catastrophe versus conspiracies that I was giving you and prove that no online static policy can be optimal for both heavy-tailed and light-tailed job sizes. And the proof is a bit technical. It's a pretty detailed change of measure kind of argument, but the intuition is pretty simple. So to do well in heavy-tailed, you have to control for the catastrophe, which means, what does that mean? It means that if an infinite-sized job arrives, you need to make sure that it doesn't make things unstable. Because if it makes things unstable, then all the other jobs will suffer. And so under first come, first serve, and if an infinite job arrives, nobody else after that job finishes. So the system becomes unstable. And that turns out to be a necessary condition for being optimal in heavy-tailed, is you have to make sure that if an infinite-sized job arrives, things stay stable. Under SRPT, an infinite-sized job doesn't affect anything, right? So an infinite-sized job just sits at the back of the queue the whole time. It only gets work when no one else is present. Everything finishes nicely. So that's necessary here. But under light-tailed, you actually have to make sure that no matter what, every job gets served at a sufficient rate, where sufficient is proportional to its size. And that's basically to make sure that no combination of jobs that are a little bit larger than normal can cause instability. And clearly you can't do both at the same time.
I still don't understand the intuition that why SRPT is worse on
so why is it?
Why it doesn't work?
Yeah, so that's true. I didn't give you any intuition for that. So it doesn't work because. So what's the good intuition? So think of the exponential case and what the tail of SRPT looks like. The large job under SRPT is going to have a much worse behavior than the large job under first come first serve. Right? So that's pretty clear. And now the tail of waiting time is going to be impacted by those large jobs. And it's going to be impacted dramatically, right? Because they're going to get stretched out quite a bit. And so there's one of the intuitions is that if you satisfy this, your tail is going to behave like a busy periods tail. And if you satisfy this, then your tail is going to behave like a workload tail. And first come, first served behaves like a workload, which means that under light-tailed it does well, but under heavy-tailed it does bad. And SRPT behaves like a busy period, which means that under heavy-tailed, since the busy period doesn't depend on the higher moments, it does well, but under... Yeah.
The first one is clear, the second one is confusing.
It's confusing, yeah. We can talk more after. Okay, so the thing that I think I want to highlight the most about this is I think this impossibility result is an opportunity, because what it highlights is it tells you a lot about the structure that leads to the bad, the inability to have robustness in the worst case results, and it gives you an idea of how to learn. You don't actually have to learn too much to do well. And these sorts of learning results. So in the stochastic model, the follow-up to that impossibility that I just mentioned is actually that all you need to do is learn the load, and you can be optimal in both most of the time. So you don't need to learn the tail. You don't need to learn some complicated thing about the distribution. You need to learn the load, and then you need to share and basically do a hybrid of PS and first come, first serve, where the hybrid depends on the load, so that you make sure that each side can maintain stability appropriately. And so learning something very simple can get you robustness within the stochastic framework. And I think that you should be able to take this intuition and do something like this again in the worst case framework. What is it that is enough to learn about the instance to be able to get around the hardness results, around LP norms and these other things? So I think there's a lot of insight in these sorts of arguments that can connect to the worst case set. Okay, so that's basically what I wanted to say there. And I think conspiracies and catastrophes, really the idea is that controlling for both of those is very hard. And this is, again, something that we looked at in terms of tails, but it shows up in lots of other scheduling problems. And I think there's insights there that can connect between the worst case and the stochastic side. I'll stop there. Thanks.
So I think before taking questions, a quick reminder, at 4:30 there is a lightning talk session where some of the participants will give a 5-minute presentation on open problems and their research. So you should come back for that. And yeah, if you have questions, I think we can take.
Adam? Yeah.
Is there any hope of some kind of general result translating certain arguments from one of the worlds over to the other world?
Yeah.
You mentioned a few specific cases.
Yeah. So the closest thing we have to that is Nikhil's stuff that he talked about at the end of the first talk, where if you can understand a busy period, then you can port the n to a 1 minus rho in a sort of simple models. I think there's a lot left to try to do there in terms of more general models, but that's hard. So I've been thinking about the multi-server model of that for a little while, and it's really hard to understand busy periods and some of the more general models in a tight enough way that lets you do this porting. But I think that's a really interesting direction where there's some nice results. The first part here, I think it's not a general framework, but it's a general style. Or sorry, the second one, I guess, number 2 on this list. There's a general style of result that I think we're missing that is very interesting, which is competitive results for optimal stochastic policies, or for forms of stochastic policies. And are there problems where there's still a strong competitive result for something that is motivated by optimality? And so I think results of the flavor, this is within a factor of x under stochastic assumptions and maintains a worst case guarantee. That I think can be done in some sense with techniques that we have, but it's a different style of question to ask than we've been asking. So I hope that people can look at that. And then I think heavy versus light is something that should impact worst case results more than it has. So I have some specific problems that I can mention to you about that. Other questions?
So one that I have, so resource augmentation for handling heavy details. If you give epsilon more heavy details.
That's a great question. I haven't seen anything like that on the tail side. So there's there's basically no stochastic results anywhere that say, give yourself extra capacity. How much do things improve? And it's such a common thing in the worst case world. It would be nice to see that. Oh, that's true. There's some for multi-servers. You're right.
Okay, so let's have coffee and then come back for the lightning.